Alright, so in this video we're going to get into slender columns. Just to review briefly before we do that, last time we did columns, we developed an interaction diagram, which is axial capacity on the vertical axis, moment capacity on the horizontal, and we developed that by looking at these strain conditions. We're going to use that same data, but instead the whole focus of a slender column analysis is looking at a magnified moment due to P delta, so force times an eccentricity or a deflection that increases the moment. So at the end of the day, we're still going to want to come to our final interaction curve and plot our axial and moment points from different load combinations and compare those. So at the end of the day, we use this same thing, and whether you develop this from the spreadsheet you made last semester or from RAM, that's kind of where we're headed. Okay, so slender columns. What happens with slender columns is the deflections of a building increase the moments in the column, and we're going to look at P big delta. So as the building drifts due to lateral loads or unbalanced gravity loads, that deflection creates an increased moment in the column due to the force times a distance. And so if we look at an interaction diagram, which is given by this generalized curve here, where our curve or our moment relationship, axial load relationship was a straight line, with this P delta effect, it bends. And what happens is it gets to failure because it has a higher moment and it can carry a lower axial force. So what we want to do is capture that additional moment either through a P delta analysis in a software like RAM or from a magnified moment analysis from ACI. And so jumping into this flow chart, this is out of the ACI code. It basically walks you through when we need to look at slenderness, whether we have a non-sway or a sway frame, how we manage that, what the results are. There's a limit to how much the second order or the magnified moments can be over the original. And anyway, so let's get into this a little bit more. So slenderness triggers, we looked at this last semester, but this is a little more detailed figure. If we have a non-sway frame, so often shear wall building or a sway frame, often a moment building, there's different limits based on the slenderness. So we calculate this, decide if we need to consider or not. If our sections are large enough, so cross section of a column is large enough compared to its length, then we don't need to look at slenderness. However, if it is, then or if slenderness is triggered, then we can either do an approximate method out of ACI or a P delta analysis, which is generally software based today, although that can be done by hand if you want to spend a week or so. Anyway, so I'm going to go through the approximate methods. I would say at this point, given the ability of the software to do this stuff fast, the approximate methods are becoming obsolete. Okay, so just reminding you guys on the nomograph to get the K. So it's going to be the stiffness. So if we look at the end of a column, we have the stiffness of the columns on the top, sum of stiffness of the beams on the bottom. That gives us this G. I think the concrete code, this is actually from the steel manual, the concrete code used a different symbol, same approach. Anyway, then you basically plot the line to get your K factor. All right, there's two ways to decide if a structure is non-sway. The first is if you do a P delta analysis and the moments in the end of the column don't increase more than 5%, then it's considered non-sway. If they do, then it's considered sway. Or we can use this Q equation, and if it's less than 0.05, then we can say we're non-sway. And that's given here. Section properties. So this is critical. When we're doing analysis of concrete for radius of gyration, which plugs into this analysis here, we can use gross section properties, and that's cool. But when we're actually analyzing the structure, either by hand or with finite element software, because the columns and beams crack, we need to use reduced section properties, moment of inertia really. Gross section, gross area stays the same, but we modify the column moment of inertia by 0.7 and for beams by 0.35, which is a big deal. Okay, so just keep that in mind. Anytime you model concrete, you need to go in and adjust the moment of inertia factors. So these equations are out of ACI 318. So basically the column moment, the final moment in the column is equal to delta m sub 2, and delta isn't actual deflection, it's a non-sway second order approximation factor that we multiply by the moment. They should use a different symbol, but they don't. So basically we have the CM factor over this value's axial force over the buckling strength of the column. And CM is defined here. You can kind of get into that. You can read the code sections for more info on that. Euler buckling equation. We have this EI effective, which is given down here, either this value here or this value here, which is really just an approximation on when this column cracks, what is the true moment of inertia from that. So for non-sway, we would use, this would be the approximate method. And for sway, we have something similar where we have a term that includes the non-sway portion calculated from this page, and then we have an additional factor, a sway factor, or a moment magnification factor for sway. And that's given by either of these two equations. And really they just come down to suffering through the analysis and the tracking of column forces and buckling strengths and whatnot. I do have an example put together on this. So this example I put together for both steel and concrete. For the first part, so it goes through loads, load combinations, live load reductions. This is the tracking of the column forces, and then a kind of a working through of these moments, the lateral analysis for the first story, and then this concrete magnification factor. Here I do the calcs. You can see the symbols different for the end rigidity ratio. Plot the lines, get the K factors for non-sway and sway frames. And then I can see that I'm under 100 on the slenderness, so I can use an approximate method, which I go through the calculations on this next page all the way through. So as you can see, it's pretty extensive, but this example will kind of walk you through step by step how it's done. Anyway, at the end of the day, the most effective way to do this today is in software. These images are out of RAM, so you would model the building, put all your loads, vertical, lateral loads, into the software. Two things that need to happen. You need to do this I sub G factor, so it's a moment of inertia adjustment factor. This would be for the column. I need to fix that. This would be a column factor, and this would be the beam factor. And then here we go into the analysis and say, hey, turn on P delta analysis. And the software basically looks at the deflections in a load combination, calculates the additional moment, recalculates the next iteration with that extra moment, sees how much more deflection occurs, takes the new moment and does that over and over until either it diverges and stops running or converges and gets to an answer. Honestly, this is the way to go today rather than this approximate method that just is tedious. All right, one of the key things to remember is at the end of the day, from our first order analysis, so the very first run, to the final analysis, our moments can't increase more than 40%. If they do, the code kind of caps this and says, hey, that's getting too close to a stability problem. We're not going to let you go there. So when you do a p-delta analysis, make sure you look at the initial moments in the columns, compare them to the final moments, and see if you meet this 40% increase criteria. And you can do that just by turning off this p-delta analysis. All right, so that's a key kind of final check. And then what you do with it at the end is you take this moment from the p-delta analysis and the axial force, plot those values, and see if they fall within the interaction diagram. So the whole development of the interaction diagram stays the same, whether we're looking at a slender column or not. What changes is how are we calculating the amplified moment from the deflection of the columns. All right, so that's that. Enjoy, and we shall talk more in class.